looking forward to your talk.
Thank you very much, Martin. And thanks to the organizers for the opportunity to present my work. Now, I'm going to be talking about this very recent work from last month, in which we look at correlation measures of Gaussian states in two-dimensional CFTs. Because of the time, I will only focus on the part relating to complexity of purification. But there's a lot more in this paper, and I invite you to have a look at it. So yeah, let's go. Now, this talk is going to be about the intersection between gravity and quantum information science via holography. And as many of you know, one of the main characters in this study has been entanglement entropy. And the reason is that, well, in holography, the emergence of spacetime is encoded in quantum data at the boundary CFT. And entanglement entropy has opened a way of looking at quantum information properties in holography. Now, as you all know, entanglement entropy is related to codimension 2 minimal area surfaces in the bulk. And here, what I'm representing is how this works, for example, in vacuum ADS3. And the idea behind entanglement entropy is that it allows us to reconstruct the bulk or part of the bulk from the perspective of the boundary CFT. Now, what was realized in the last 10 years or so is that, however, holographic entanglement entropy is not sufficient to determine the entire bulk geometry, in the sense that it doesn't contain all the information that you would like about a holographic state. There were some observations that actually showed that certain codimension 0 and codimension 1 boundary anchored surfaces actually capture more information than what entanglement entropy is able to capture via this minimal area codimension 2 surfaces. And it was proposed that the quantity that captures this additional information is complexity. And this quantity should capture information which is not captured by entanglement entropy. And this can be visualized, for example, if we look at the eternal Schwarzschild ADS black hole, and we remember that this is dual to the thermal field double state, which is a pure state. Now, these minimal surfaces that capture information are actually penetrating the inside of the black hole in the holographic setting, which is something that is also interesting from the perspective of information science. So, like to try to understand more in detail what happens inside the black hole. Now, these proposals originally were made for the pure states, for the thermal field double state, which is something that captures information from the two sides, from the two CFTs living on the two conformal boundaries of this space-time. And soon thereafter, there were ideas of what would be the correct quantity to look at if we're only considering one copy of the conformal field theory. And hence, there were these sub-region complexity proposals that came into place, which I will describe now. So the first one is called the sub-region complexity equals volume proposal, which proposes that the complexity of a state is captured by the volume of a codimension 1 surface that extends from either, let's say, the right boundary anchored point towards the bifurcation surface, to the bifurcation surface in this diagram. The other two proposals, namely the sub-region complexity equals action and sub-region complexity equals volume version 2.0, relate to the intersection of something that's called the Wheeler-DeWitt patch, which is this region in blue in this diagram, and what is called the entanglement wedge. In the action proposal, one evaluates the gravitational action in this patch. And in the volume proposal, one evaluates the volume of the causal diamond, which is represented by this pink shaded version. Now, this is all very good from the perspective of holography. However, the question is, what do we mean when we talk about complexity? And here is when one is tempted to compare it with entanglement entropy, because entanglement entropy followed the opposite path. In entanglement entropy, people were studying from the perspective of the CFTs before they made the connection to what happened in holography. And here, complexity follows the opposite side. So the question is, what do we mean when we say complexity on the CFT? And to this end, people realized that there was already a notion of complexity that could be taken from quantum information science. And this is something that it was already talked about in this conference by Pablo Basteiro yesterday. So I will not stay too long in the details, but suffice to say that complexity is supposed to be a measure of how difficult it is to produce or to reach a certain state called a target state. And this works via something called quantum circuits, where we have a reference state from which we start, and we apply a certain unitary transformation to it, and we get to another state called a target state. Now, one can do the analysis of what happens, for example, in a qubit system. But for the purpose of this talk, I'm going to focus on what happens when we have a large number of, when we have a continuous, trying to go to the continuum of degrees of freedom. So in this sense, we look at the unitary not made up of single gates, but rather as an exponential of more elementary operations. And this unitary operator can be written as this path-ordered exponential, where we have certain gate generators which form a closed algebra, and we have some parameters that are related, that are the tangent vectors of this unitary operator. Now, typically, when people talk about complexity, we fix the reference state to be something that is rather simple, say, for example, a spatially unentangled state, much like this. But in principle, it can be whatever state one chooses it to be. And now, once we have this circuit and once we have this reference and target state, we need to define a depth of the circuit. How long is this circuit? And to do this, in general, we need to define a cost function, which is going to tell us precisely how are we measuring the distance between these two states. And this is going to be, in general, some functional of the position and the tangent vectors. Now, the game, when it comes to complexity, is to extremize the circuit depth for a given choice of the cost function. And that will yield the complexity of this unitary for the reference and target states. And of course, different choices for this cost function will yield different measures for the circuit complexity. And there are many examples of what kind of cost functions one can choose. The one that's going to play a significant role in what I'm going to tell you is the L2 norm. And one of the reasons for it is that it corresponds to obtaining complexity in this setup where the cost function is an L2 norm is analogous to finding geodesics in a Riemannian space. So complexity acquires a geometric meaning in this sense. Now, this is all very good. Now, but one thing that I mentioned before is that I was dealing with pure states. And one natural question that people can ask, or that we can ask, is there a notion of complexity that works also for mixed states? Or what notions of complexity for mixed states can we find? And one of these notions is called complexity of purification. Now, the idea with complexity of purification is that once we have a mixed state that is given by some density matrix rho A that lives on some Hilbert space, we're going to enlarge this Hilbert space with some ancillary system, let's call it A prime. Now, of course, there will be in principle an infinite number of purifications, let's call them psi t, which live on this enlarged Hilbert space, such that once we trace out the ancillary degrees of freedom, we will recover the original mixed state in the first Hilbert space. Because of this, we're going to define complexity of purification as the minimum of the complexity functional with respect to some reference state and to all possible purifications psi t. This means, of course, that in principle, we can think of purifications that have more degrees of freedom than the original one, and that could be the case. Now, how can we think about this complexity of purification and what it means? So suppose, for example, that we have some mixed state, rho Ta, who lives in some Hilbert space. And there's also some mixed representation of a reference state that also lives there. Now, once we purify these two states, there will be a representation of the reference state in this enlarged Hilbert space where it's a pure state. And there in principle is going to be not only one possible target state, let's call it psi t, but there's also going to be a family of target states that are related to each other, say by unitaries. So there's also some freedom when it comes to choosing the target state in this setup. Now, and complexity purification will then be exactly choosing what representative of this family of states is the one that has the minimal distance to this reference state. Now, one of the things that we can do is we can deal with very special states in quantum field theory. And naturally, there are some states which stand out, for example, Gaussian states. And Gaussian states with vanishing one-point functions are very interesting from the point of view that they are ground states of free QFTs. And the feature that they have is that they are completely characterized by their two-point functions. And these two-point functions make up what we refer to as the covariance matrix. And the entire information about a state which is Gaussian is captured entirely by this covariance matrix. So for example, if we have n degrees of freedom, then the covariance matrix, we will write it depending on whether we have a fermionic or a bosonic or a fermionic system, we will write it in this particular way. And because we're dealing with these degrees of freedom that are this dimensionless phase space operators, there is a natural group of symmetries with which we will deal with, which is the symplectic group. So for example, if we, oh, by the way, in the covariance matrix for the bosons, we will basically look at the anti-commutator, so with the plus. And for the fermionic Gaussian states, this covariance matrix is built up from the commutator, which is the minus here. Now, for example, if to have an idea of what this covariance matrix looks like, take, for example, a one harmonic oscillator and take the ground state of the harmonic oscillator, which looks like this. Then the covariance matrix will have this very simple form. And when it comes to complexity, one is able then to rephrase the problem of finding the optimal circuit from the perspective of, say, the wave function to the perspective of the covariance matrix. So in a sense, the complexity can be recast as a function of the spectrum of this covariance matrix. So for example, what happens with a system of two harmonic oscillators, and this is something that appeared as part of this project, where we look at what happens with quantum quenches, and in this setup we were looking at systems of two harmonic oscillators, which followed different quench profiles through a critical point. But in order to visualize how this all connects, this level, for example, consider the covariance matrix of these two harmonic oscillators. We will have one harmonic oscillator that will be labeled by A, and say we will have another one that will be labeled by A bar. Then the covariance matrix will be a 4x4 matrix, where the entries will be referring to these correlators as we see them labeled here. Now, it is also interesting to compare what entanglement entropy is sensitive to in this case. If we take these two harmonic oscillator systems, say that's going to be in a pure state, then once we trace out one of the oscillators, then we will have only one of them, and hence the entanglement entropy will only be sensitive to, say, for example, this blue portion of the covariance matrix. In other words, it will be determined by the spectrum of what happens to this reduced density matrix for one of them. On the other hand, pure state complexity, if we take the two harmonic oscillator in a pure state, will be sensitive to the information pertaining to the whole covariance matrix. And if we look at what happens to the complexity of either one of the oscillators, then it will again only be sensitive to information either to A or to A bar. Now, what is interesting about this is, of course, in order to consider the complexity of purification, what we do is we fix the information, say, of this blue block. We enlarge the Hilbert space with ancilla that gives us these kinds of correlations, and we minimize over these. Of course, in principle, one can purify a mixed state made up of one harmonic oscillator with as many as one wants. But it turns out that it's only necessary to do it with one more harmonic oscillator. In a sense, these purifications that one does in practice are often minimal. And one very interesting observation that can be done in this at this moment is that the complexity, or rather complexity of purification, satisfies what's called as a subadditive property, which is something that it brings us back a bit to the holographic complexity proposals. It is interesting to mention that from the three proposals, the action and the volume satisfy this subadditive property, volume 2.0, sorry, but complexity equals volume does not satisfy this subadditivity property. Now, this is all fine, and this is for two modes. But then the question is, how can we really exploit these, the notion of Gaussian states? And one very interesting thing that we can do is, of course, we can go beyond this simple two-mode example, and we can actually go for the full to larger subregions of the vacuum state of free CFTs. So, and this is the main topic of our paper that I was mentioning at the beginning. We focus on two paradigmatic CFTs. We focus on the Klein-Gordon field in the massless limit, and we focus on the critical transverse Ising field model on a circle. So what is interesting is that the vacuum states of these theories are Gaussian. So this means that we can treat them with using exploiting their symplectic structure of the symmetry that their covariance matrices have. Now, what we will do and what I will show you is basically what happens when we consider subregions that are going to be made up of a fixed number of sites. And in principle, we would consider a subregion consisting of only a fixed number of sites, or two adjacent regions. In principle, in a discretized lattice model, one could also consider what happens as a function of the distance or the separation, the lattice separation between these two systems. And there are certain subtleties, which I will probably mention at the end of the talk. But what's interesting is that we can take the ground state or the vacuum state of these two theories, which is a Gaussian state, and we can take subregions of this Gaussian state and then consider how complexity of purification behaves for these subsystems. Now, just to show how these covariance matrices look like in this case, here is, for example, the first one, which is for the critical transverse Ising field model. after doing the whole Jordan-Wigner transformation to bring them into fermionic variables and writing the covariance matrix in terms of Majorana modes. And the second one is the covariance matrix of the Klein-Gordon field. And you can already notice that the Klein-Gordon field is going to be more rich in structure because there are basically many parameters that come into play, for example, like the mass and the lattice spacing, which is something that in the critical Ising field model, which we do not have. Now, of course, this is nice. We have these covariance matrices, but how are we going to measure distances in this setup? Now, we're going to be using an L2 cost function, which is, again, based on the geodesic distance. And in this case, we will consider that the reference state is going to be a spatially unentangled subregion in the same spirit as the one that I showed before. And our target state will be the vacuum subregion. And the idea is to minimize this cost function over the most general Gaussian minimal purifications. So for example, when we take just a single interval of size W over D, we find these two answers for, on one hand, for the bosonic CFT, we find the divergent structure of complexity looks like this. Now, it is interesting to see that there are terms which are, well, of course, there's going to be a 1/2 because basically because of the square root that appears here in the L2 cost function. But if we look inside this square root, there's a linear term and there's a logarithmic term. And in the case of the bosonic theory, the coefficients that come in front of these different divergent terms depend on the mass of the field and also on what's called a reference scale, mu. This is basically one has the liberty of having an arbitrary reference scale for spatially unentangled subregions in the bosonic case. This is not the case for the Ising CFT, where these coefficients that appear here for complexity of purification are basically just numerical values. One is tempted, of course, to compare, for example, with entanglement entropy. And in principle, what one should expect that there's a central charge appearing here somewhere. The subtlety, of course, is that, for example, in the bosonic case, there's the dependence on these parameters, like the mass and the reference scale, is hardly trivial, and it's actually still a matter of study of how complexity or complexity of purification and entanglement entropy are related. So this is what happened for a single interval. Now, it's also interesting to see what happens for adjacent intervals. Now, in order to consider adjacent intervals, we need to do some sort of regularization that is akin to, say, for example, mutual information. And then, of course, one gets naturally the notion of mutual complexity of purification. And the notion that we will be considering, or the combination rather that we will be considering, is this one here, which is taking the squares of the individual intervals and then subtracting the complexity once we take the two intervals together. And of course, people who are familiar with the behavior of mutual information for adjacent intervals in the vacuum will realize that the behavior is surprisingly similar, strikingly similar in both cases for the fermions and for the bosons. And in this case, one also recognizes the divergent structure of complexity of purification in this setup. And once again, one sees the same coefficients that appeared in the, well, first of all, the linear term disappears, which is something that is not that one should expect just by considering this combination. But this term here, this log terms, which appear both for the fermionic and the bosonic complexity of purification, are also the terms, the divergences that appear for mutual information. Whereas, of course, as I said before, the coefficients are more complicated than just the central charge. Now, of course, once we have this, it's it's all good, but can we actually make some comparisons with these holographic subregion complexity proposals? Is there actually something that is being captured by these Gaussian states in these free CFTs? And strikingly, the answer is, well, there's actually a very interesting comparison that we can make. And people have studied what happens for the single interval in these holographic subregion complexity proposals. And one obtains basically a similar divergent structure where there's a linear term and there is a logarithmic term. You'll see again that I'm not mentioning here the complexity equals volume proposal, because that one is, I would say, and please don't quote me on this, even though you're recording the talk, it's rather too simple in this setup to actually capture what is happening at the boundary. But for complexity equals volume 2.0 and for complexity equals action, we actually see not only in the single interval case, but also in the adjacent interval case, the very same divergent structure as we found for complexity of purification. And of course, here for complexity equals action, there's obviously things appearing like there's counter terms that one needs to take into account in order to actually do the computation. And this is captured by this LCT. L is simply the ADS radius. And of course, one other thing to notice is that for the adjacent interval case, this mutual complexity that people usually consider is done without the squares. And this is also something that is related to the fact that people have observed that when it comes to complexity from the quantum field theory side, what's called the L1 norm is closer, quote unquote, to holographic proposals because one does not have this square root over here. So one has a more direct comparison with holographic proposals. The difference is that the L1 norm is very difficult to minimize or to optimize. Whereas for the L2 norm, there's very powerful techniques like the one that we used in our work, where one can efficiently obtain the minimum of the complexity functional for the most general Gaussian purifications. Now, just to finish, I just want to mention a few things that I've said throughout the talk and finish with some remarks. Now, it's interesting to see that complexity indeed captures more information about a quantum state and entanglement entropy, although this is probably an unfair comparison. One should compare entanglement entropy with complexity purification. The other observation is, of course, that because vacuum states in free CFTs are Gaussian, then we have a full description of the physics in terms of their covariance matrices and the real symplectic group. And furthermore, it's also striking that the vacuum states in these free CFTs actually capture that we can actually get some universal properties from them, because complexity is a quantity that inherently depends on many choices. But nonetheless, it's striking that we can actually obtain some universal results from them. What I mentioned also, and as you can see from the plots that I showed with the adjacent cases, complexity of purification seems to be subadditive, and this seems to be a very general property of complexity of purification, and which matches very well with the expectation that people have in holography. And of course, this is related to the fact that, well, one wishes to actually make a comparison with these holographic proposals. And then the question is, what is not captured by these Gaussian states? And one thing that is not captured by these Gaussian states is, for example, what happens when we actually take disjoint intervals. It's easier to think about it from the perspective of the fermionic theory, where the notion of locality is non-trivial once we consider disjoint intervals. And for adjacent intervals, there's a spin picture and a fermionic picture, and they both agree. And the calculations that we get are perfectly fine, and the states are Gaussian. But once we separate these two subsystems in the lattice, the description of the covariance matrix turns out to be non-Gaussian. So there's something that we cannot capture from just looking at Gaussian states. So not only that, but also if we look at non-Gaussian states, there is the hope that we can work towards obtaining something about complexity in actually interacting theories, because one should remember that holography works for strongly coupled CFTs. So far, all the work that has been done and everything that I've shown you has been done for free CFTs. So of course, it's interesting and it's an active field of work to study what happens in interacting theories. And a step in that direction is to look at non-Gaussian states. So that's why one of the things that we're doing is looking at how do we go beyond Gaussianity. And of course, finally, one would like to say, well, the correct description of complexity from the boundary perspective is this one, and it matches with this holographic proposal. Though I think that we are still far away from this, I think it's something to keep us all motivated into looking at complexity, which is a quantity that will surely still be relevant in the following years. And with that, I thank you for your attention, and I'm happy to take any questions that you have.
Yeah, thank you very much for your nice talk. So are there questions from the audience? So let me start. I've got a maybe silly question. If you look at your complexity of purification for a single interval, and like the result you quoted for your bosonic theory, so you say this F2 only depends of mu times delta, but not on m divided by mu. Is there?
That seems to be the case. We cannot think of a reason why this should be the case. So far, this is only a numerical observation, but it's I mean, we would like to actually understand why it does not depend on the mass. And of course, one thing that we try to do in order to actually make it a CFT is obviously to get the mass to zero. But for a non-zero mass, there's actually still some tiny mass dependence in these coefficients. But yeah, I mean, we don't understand why the linear term doesn't have this mass dependence.
So, and which of those quantities should I view now as being universal or as being observable? Because they are multiplied by, say, divergent quantities like omega divided by this delta.
Right. I mean, in the sense that the universal properties are actually these divergent pieces, like this linear divergence and this logarithmic divergence, which is also things that one sees, for example, in the usual holographic complexity proposals. One also sees these kinds of divergences which appear in very particular ways. For different number of dimensions, they appear. So these are precisely the universal properties that complexity of purification has, and yeah.
But there it was like that these kind of divergences somehow were fixed relative to each other. At least the result you quoted, there was a 2 and a 1.
Yes.
So, and this seems to be not the case now for your bosonic CFT, because like F2 doesn't depend on m divided by mu, while at least you quote that F1 depends on m divided by mu.
Yes, that is correct. And I think one of the reasons why is that there's no understanding of what, say, the reference scale plays in these holographic settings. I don't think so far people understand what the role of the reference state is at the level of holography. In CFTs and in QFTs, it's natural to consider a reference state where one has this scale appearing naturally, but to actually understand what this reference state scale or reference scale corresponds to in holography is still not understood. So you're right, even though the divergent structure is comparable in the sense that the same kind of divergences appear, a linear and a logarithmic one, the coefficients are the things that we still don't know how to interpret on this side, I would say.
But you think there is a choice of reference scale so that you can also reproduce the holographic?
Well,
or you say we have to somehow still modify our proposals on the holographic side to have these features?
well, my personal choice, and I don't think this is something that's common in the community. The action proposal seems to be richer in the sense that one has this counter term action that appears in the computations, and one has this counter term scale. Now the question is whether there is some correspondence between this counter term scale and the reference state scale at the boundary. I don't think it's that clear, and I don't think that's quite one-to-one comparison. Yeah, I would say that we don't understand how the reference state enters holography. Yeah.
Okay. Are there further questions? So that seems to be not the case. Then again, thank you very much for your really nice talk, which I enjoyed.
Thank you, Martin.